Alright, hello everyone. My name is Tristan Hagerman, and I will be giving the application presentation today for Thursday, October 18th, 2018. Um, as we know, Professor Free gave a presentation on Tuesday. The class was about admissible regions, so I'll be covering that topic today as my application. So, as Professor Free mentioned, this concept was introduced by an Andrea Milani. Andrea Milani, Professor Milani, is a professor at Pisa University in Italy, or UniP. The Pisa University is an Italian public research university, and during my research I found out that it is the 19th oldest extant university in the world, as it was established in 1343. Professor Milani is within the Department of Mathematics at the university. He is a mathematician and astronomer, and as a hobby he likes to write science fiction. He is also a member of the Italian Society of Celestial Mechanics and Astrodynamics, or SIMCA, and therefore within that he is a part of the committee that studies the dangers of possible impacts with the Earth, which directly relates to his first paper regarding admissible regions, which was published in 2004. So, as he mentions in the paper, around that time there was an enormous increase in the rate of asteroid discoveries due to automated surveys. Automated systems would point at a specific region of visible space and would take in digital images over a short time span, which he specified was about 3 to 5 images over a 2-hour span. And if between those images over that time span an object was seen to move in a straight line with a uniform velocity, it was assumed to be a real object. Which he says that method is optimal for detecting asteroids and comets, knowing that they are asteroids or comets, but it does not give us any really useful information on determining the orbit. And this is due to the fact that the curvature created by those three observations appears as a divisor using Gauss's method. So over that short time interval, without much movement between observations, there's a much smaller curvature created by the method, so that the orbit that is produced by Gauss's method is much less accurate because of this. Now, that time interval can be increased, but that would require us taking observations over multiple nights. And in doing so, we can be less certain that the objects that we are observing from night to night are indeed the same objects. So he specifies an approach to lowering the lowering the uncertainty between those observations. So first, from the observations on the one night, a very short arc is produced. From that VSA, very short arc, you can produce an attributable, is what he calls it, which consists of the reference time, 2 average angular coordinates, which are right ascension alpha and declination delta, and 2 corresponding angular rates, which are, in our case, alpha dot and delta dot. He specifies that it may or may not contain an apparent magnitude. Those observations don't give us a range or a range rate, R or R dot, but we can produce a set of conditions to bound potential ranges and range rates. So in this paper, since he's concerned with asteroids in the solar system, he specifies that the asteroid is assumed to not be in an Earth orbit, so its orbital energy is greater than that for an Earth orbit, but it is in a stable solar orbit. So using these constraints, he produces curve A, which is greater than the energy for an Earth orbit, which is this curve A. And he specifies that the radius r has to be outside of the sphere of influence of the Earth, which he calculates to be, I think it was 100th of an astronomical unit, which is this dotted line B, which gives us this region out here. To further define this region, he specifies that the energy has to be less than an energy for a solar orbit, so that the object does not escape the solar system, which gives us this curvature, just for an arbitrary example. And then as a final restriction, he specifies that the radius has to be greater than our Earth, such that the orbit is not intersecting with the Earth, which gives us his final dotted line D. And using these bounds, he creates this region here, which is considered to be the admissible region. for the orbit. Now, as he specifies, C can create either one component, as we see before here, or it can create two separate but connected components, as we see in this. But I'm getting ahead of myself. After he first describes this method, he states his assumptions. Using this method, it's not topocentric, it is a geocentric observer system, and it avoids a three-body problem by a number of different ways. It completely avoids other bodies, including the moon, which he says may or may not be valid, but is good for a first approximation, and he completely neglects the eccentricity of Earth's orbit when calculating the energies for these orbits. After these assumptions are stated, he continues to refine his A, not a satellite of the Earth energy, and C, not a satellite of the solar system energy, which he then, by continuing to refine that region C, he proves that it's either one or two connected regions. And then he goes on to further analyze close approaches, which are R is between the R Earth and R sphere of influence. And this results in this curvature that we see here that I believe Professor Free showed us in class. So this is R and R dot, and this is log R. So this zero line here shows the zero energy for an Earth orbit, so anything to the right of this region is considered our admissible region, and then he shows 3 lines of equal energy for a Sun solar orbit, which is 0, 2e to the minus fifth, and negative 2e to the minus fifth, which gives us this curvature. And then the sphere of influence is this dotted line, so basically anything within this region is what he considers to be the admissible region. So he continues on to give a specific example for the paper, which uses asteroid 2003 BH84. He uses just the first 4 observations over the hour and 40 minute of the night that it was discovered, which resulted in a 0.35 degree per day movement. He found his attributables by a linear fit method, and then he created his admissible region using the algorithm that he described previously in the paper. And then after modifying that the semi-major axis of this asteroid would be less than 100 astronomical units, he found that the maximum value for R on that night was determined to be 4.46 astronomical units, which gave him this admissible region here. He shows that the actual value that was determined is this little cross here on these plots. And then the final section of this paper, as Professor Free mentioned, giving this admissible region, it lowers our potential R and R dots, but it still has an infinite number of points that could be true. So he specifies how you can go about distributing nodes along the curvature and then within the admissible region, which can then be used as samples to determine potential orbits here, which Professor Free in her lecture shows us in a more three-dimensional way. She showed us how at a single line of sight with different assumed R's and R dots, how those final orbits would look in 3 dimensions. And with that, I would like to finish my presentation. Thank you.